Welcome to this talk. I'm Stefan Feyer and I will present our work 2D, 2.5D or 3D, an exploratory study on multi-layer network visualizations in virtual reality. I start here with a definition of a multi-layer network. A standard graph is described by a tuple of vertices and edges. Additionally to standard graphs, multi-layer networks have layers, here denoted as L, and we allow the vertices to belong to a layer. Consequently, the edges hold the information about the layers as well. When visualizing multi-layer networks, the question arises of how to arrange the layers to efficiently support task solving. There are various possibilities to arrange the layers of a multi-layer network. Until now, there was no research about the effectiveness of those layer arrangements. The three main visual metaphors are 2D, where the layers are located on a plane, 2.5D, where the layers are stacked, and 3D, where the layers are located in 3D space. We decided to investigate on this topic for node-link representations of multi-layer networks in virtual reality. So in our work, we tackle the question, what is the effectiveness of 2D, 2.5D, and 3D layer arrangements for node-link visualizations in stereoscopic virtual reality settings? To answer this research question, we first decided for a translation of those visual metaphors in a representation for a virtual environment. In 2D, we located the layers on a horizontal plane. For 2.5D, the layers are horizontally stacked, and in 3D, the layers are located on half a sphere. We took tasks from the task taxonomy for multilayer networks by McGee, which consists out of 4 categories. Category A comprises tasks for entity connectivity across layers, Category B, entity comparison across layers, C, layer structure manipulations, and D, layer comparison. However, in our work, we focus on the categories A, B, and D, from which we chose 2 tasks each. We ran an experiment where our 22 participants solved the 6 tasks with the 3 layer arrangements. Additionally, the tasks are solved in 2 complexity levels with 3 and 7 layers. We measured the error rate, the movement the participant performed, and the task completion time. This is how the experiment looked like. A panel is located at the wall of the virtual environment. The participant reads the question and then press Start Task. The graph appears, and the participant is searching for the answer of the question. We see here a multi-layer network with 3 layers in the 2D layer arrangement. As soon as the participant presses End Task, the graph disappears, and the answer can be chosen at the panel. I will present here 3 tasks as an example. In task 1, the participant search for a shortest path between 2 highlighted nodes, which are located on different layers. Here we see a multi-layer network with 7 layers in the 2.5D layer arrangement. In task 2, the participants determine the layer with the highest degree, which means to identify the layer that is connected to most other layers. Here we see a multi-layer network with 7 layers in the 3D layer arrangement. In task 5, the participants determine the layer with the highest density. In this case, on a multi-layer network with 7 layers in the 2D layer arrangement. In task 3, the participants search for a highlighted connectivity pattern on the other layers. In task 4, the node with the highest degree is to be found. And in task 6, the layer with the most connected component is to be determined. This is the data we collected for each task. Here as an example is the data for task 1. The error rate is lower for the higher dimensional layer arrangements for networks with 3 layers. The same pattern can be observed for multi-layer networks with 7 layers. Furthermore, we can see that the task completion time is nearly on the same level, but slightly higher in 2.5D on networks with 7 layers. The movement performed is higher with the 2.5D layer arrangement for both networks complexities. It seems that higher dimensional layer arrangements perform better for shortest path problems. In task 5, the participants determine the layer with the highest density. On networks with 7 layers, the error rate is highest with a 3D layer arrangement. The task completion time is also highest in 3D, and the movement performed is higher in 3D than in 2D. This indicates to avoid 3D layer arrangement for multilayer networks with 7 layers. Let's step to the results. Our initial hypothesis was that certain multilayer network tasks can be performed faster and more accurately with 2.5D and 3D representations. In particular, the 2.5D concept corresponds to the frequently used mental model of layers in a multilayer network. Consequently, we expected that the best result will be associated with 2.5D and 3D representations, and that these would also scale better for large networks. As we will see, we could not entirely confirm this initial hypothesis. In the 2.5D layer arrangement, the movement performed was mostly higher than in 2D and 3D. This is because of the nature of the 2.5D layout, which makes the graph physically long. This correlates with higher task completion times, but not with higher error rates. The participants stated that it is hard to say what their favorite layer arrangement was because it depends on the task. They like to walk through the layers of a 2.5D graph, but because of the amount to move, the layers are harder to compare. We expected that an increase in the complexity of networks from 3 to 7 layers would result in increased error rates, completion times, and movement. The results, however, are not perfectly clear. With 6 tasks times 3 layer arrangements, we have 18 cases in total. The error rates were higher for 7 layers in 12 cases and higher on 3 layers in 4 cases. The movement performed was always higher with more layers, in 8 cases statistically significant. The task completion time was also higher with 7 layers. So, which layer arrangement should we use? We could identify tasks that benefit from specific layer arrangements. For multilayer networks with 3 layers, task 1, 4, and 5 benefit from higher dimensional layer arrangements. Task 3 and 6 work best with a 3D layer arrangement. For multilayer networks with 7 layers, task 1, 4, and 6 benefit from higher dimensional layer arrangements. Task 2 and 3 perform better in 2D, and for task 5, 3D layer arrangements should be avoided. Our results show that there is no clear overall winner, but we got valuable insights about the layer arrangements for multilayer networks. Although 2.5D matches our known mental model of multilayer networks, 2.5D does not consistently outperform the other layer arrangements. Additionally, at least one task per task taxonomy category can be performed better in higher dimensional layer arrangements, and 3 out of 6 tasks can be performed better in 2.5D or 3D for both complexity levels. Furthermore, the layer arrangement does not impact scalability. Solving tasks on larger networks tend to require more time and more movement. Finally, the 2.5D layer arrangement requires more movement, but there is no correlation with higher error rates. Overall, the choice of the layer arrangement depends on the task and the network.